Hi, this is Mrs. Slater. Quote of the day, "Quiet people have the loudest minds," by Stephen Hawking. 11.7, ratio of areas. So we're going to find the relationship between ratio of the sides to perimeter and area, all about similar polygons today. So if we're going to find the area, we've got base and height, so this is not going to be too bad. We're going to go ahead and find the area of the first one. So we'll call this our first one. This is our second one. Area of the first is 1/2 9 times 6, and we get 27. And we're dealing with units, so I guess inches does not apply here. Okay, and then the area of the second one is area, and then 6 times 4, which we get 12 units squared. Okay, so let's go ahead and look at some comparisons. And the ratio of the sides you can see as a 9:6 ratio, or 6:4, which both of them reduce to 3/2. If you look at the perimeters of all of them, and as of this point, we don't have the perimeters, so we could actually find it by Pythagorean theorem on both of them, but you will come to find out that the ratio of the perimeters is going to also be 3/2. So pause, and I want you to go ahead and do the Pythagorean theorem and come up and go ahead and check. So as you found out, 3/2 is coming up again, because those are going to cancel out and you get 3/2. So the ratio of the sides, ratio of the perimeters, exactly the same. So then if you find the ratio of the areas, which is what we did in part A, 27/12, there is a 3 in common. So we're going to take that out, and you get 9/4. All right, we'll look at what is the relationship between the two of them. Okay, so we have the sides and perimeters, and what it comes down to is you can see that you can square both the 3 and the 2, and you get 9/4. So you may want to push pause and go ahead and write the theorem down. It says, if two figures are similar, then the ratio of their areas is equal to the square of the ratio of their corresponding segments. All right, so let's go ahead and move on to, I'll just go ahead and get that out of the way up there. Let's go ahead and move on to the first example. Okay, this one, it is talking about the ratio of areas of similar hexagons. Okay, so if they're giving you the areas are 22/12, we first are going to need to reduce that. So you get 11/6. Now, if they're going to want, so those are the sides, so they want the area. So what we're going to have to do to that is square the top and the bottom. So what the areas would be of these hexagons would be 121/36. Now let's go on to the next example. Part of this first one and 2A, one thing that's given that's not in the picture is that this is a right angle. So if that's a right angle, that means this is the height of the triangle. And with all these congruent marks, let's go ahead and call all of those B. And if we know that the area of the first one is 1/2 base times height, and we know the area of the second one is 1/2 base times height, you can see that they're the exact same. So the ratio of the areas would be a 1-to-1 ratio. Okay, and then on the next one, if we have parallel lines, that's going to create alternate interior angles. We also know vertical angles are congruent. And if they are all congruent, then we have similar triangles because of angle, angle. And then we can set up a proportion. So 12 is to 20 as 3, or no, not as 3 is 5. We can go ahead and reduce that to 3/5. And 3/5 squared is going to give you 9/25. So that would be your answer for the ratio of the areas. All right, so let's go on to the next one. Okay, so we have a 5-to-2 ratio, and we are given an area. So if we know all of this, then we can say that the sides squared are going to give us the ratios of the areas. So if we know that the smaller one is 2, we're going to put that on in the denominator, and then we'll just call the top x, because that's what we have to find out. All right, so this is 25/4, and with a little bit of cross multiplying, we get x is 250, and we do not have a unit, so we'll just say units squared. Okay, and then on the next one, they are giving us that the side or the areas this time are 16 and 49. And so if we want to find the area or the ratio of the sides, we would take 16 over 49 and just go ahead and take the square root of it. So I can get rid of that parenthesis, take the square root of both of those, and so the ratio of the sides has to be 4/7. So we're going to finish with this last one where AM is the median of ABC. So I'm going to go ahead and put my congruent marks in there and label them both with little b because those are going to end up being our bases. And we're supposed to find the ratio of the triangle ABC in comparison to ACM. Okay, so one thing we're going to have to do is an auxiliary line. Let's go ahead and draw a perpendicular straight down, creating an altitude, which is also the height of our triangle. And if you look at triangle ABC, then you know that the area would have to be 1/2 2b from here to here, 2b times h. Okay, and then if we're dividing that to find the ratio of the areas, ACM, the area of ACM, and I could make those areas, not triangles, area of ACM is going to be 1/2, and this one only has a base from here to here, so that's just going to be a b, which is h. So as you can see, everything is going to cancel except for 2. So it is a 2-to-1 ratio. Okay, so in summary, there is a theorem that represents this type of triangle, and it looks like this. Go ahead and push pause and write that down. Oh, excuse me. Sorry about that. Okay, so this theorem, a median of a triangle, divides the triangle into two triangles with equal areas. So if it's in a 2-to-1 ratio, that means that the two areas themselves, like this one, the black one, and the red one, are going to have the exact same areas. Okay, so let me finish with the joke of the day. The person who makes it doesn't need it. The person who buys it doesn't want it. The person who uses it doesn't know they are using it. What is it?